think we can start the last session of the conference with two nice talks about two very interesting projects. The first one is MADMAX. So we have Bernardo Santos, that he will give a talk on searching for axion dark matter with a dielectric haloscope. So,
okay, thanks. Okay, so what I'm going to talk about after a small motivation is the concept of dielectric haloscopes. Then I will introduce you MADMAX, which is a collaboration that is trying to build one of these dielectric haloscopes. And then at the end, I will tell you a little bit about one of our prototypes, CB100, which we took to CERN this year and which we used to take data for the first time. So in terms of motivation, it's quite clear. Axions are a very good candidate both to solve the strong CP problem and to unveil the nature of dark matter. Post-inflationary scenarios favor axion masses of the order of microelectron volts, and this still constitutes a largely unexplored part of the parameter space, which we hope to be able to reach with these dielectric haloscopes. So the working principle is the Primakov effect. So axion conversion inside a very strong magnetic field into photons, and these will be microwave photons in the range of gigahertz. So we have our effective Lagrangian, the part of electrodynamics, plus the added axion scalar field with its interaction with photons. And from here, one can get the equations of motion through Euler-Lagrange equations. And this constitutes a new set of axion Maxwell equations, which basically are the same as the Maxwell equations, but they add this effective charge and effective current, as well as this equation of motion for the axion field, which is also coupled to the strength of the interaction. So apart from this, we are interested in dark matter in the range of microelectron volts, 100 microelectron volts. We know that axions, if they are called dark matter, they will have velocities around 10 to the minus 3. And this means that the de Broglie wavelength for this type of axions will be around 10 meters, which means that for small regions, we can consider that the field is homogeneous. And so with this and with the previous Maxwell equations, we can get a direct relationship between the frequency and the mass of the axion, as well as a new field which appears from this interaction with the axion inside the magnetic field, which we reference with this E0 strength, and which is also proportional to the inverse of the dielectric constant of the medium in which it is. And so what this means is that inside this strong magnetic field, there will be a conversion of axions to photons, and there will be this electric field that is induced, which goes like the axion field. And the idea is that we can introduce a dielectric layer. And since there is a different dielectric constant, there will be a discontinuity at the interface. And what this means is that the boundary conditions are not fulfilled. So the system will in order for the boundary conditions to be fulfilled, the system will emit electromagnetic radiation on both directions of the interface to compensate this discontinuity. And so the idea is that one can have such an interface and then try to detect the electromagnetic radiation that is emitted from the surface. So the simplest example is the example of an interface between a mirror and vacuum. So effectively, one can think of a mirror as a dielectric with dielectric constant infinity. The vacuum will have a dielectric constant of 1. So there's a big discontinuity there, and there will be emission of radiation away from the mirror if there is a strong magnetic field inside. And so for a 10 Tesla magnetic field, we can calculate the power per unit area, which is going to be on the order of 10 to the minus 27 watt per square meter, and then input this in our signal to noise ratio and see what we get. And so for masses of around 100 microelectron volts, for system temperatures, yeah. Okay.
Why is the system particularly sensitive to 100 micro EV? Since this is not a cavity thing, is it?
Yeah. I will get.
Oh, sorry.
So we are just trying to look at how this looks like in this mass range. And so again, if you have these masses, if you have temperatures of 8 Kelvin inside the 10 Tesla magnetic field, you get a signal to noise ratio of the order of 10 to the minus 4. And so, of course, this is too small to detect and to claim a discovery. You'll basically not be able to see anything. So you need to improve this. And the way you can do it is have your system and then add a bunch of dielectric discs in front of it, which will both increase the number of coherent sources. So you will not only have emission of radiation from the mirror, but now you will have emission of radiation also from your dielectric discs. And then if you place these discs in certain positions, you'll be able to, for certain frequencies, enhance the power arriving to your receiver by a factor beta square. And so this beta square is what we call the boost factor, and basically it tells you how much, what the factor of enhancement is compared from a single mirror to a bunch of dielectric discs. And this will, for fixed positions, depend both on the dielectric constant of all your discs and also the frequency that you are trying to observe. So this is what the system looks like. If you make a small scheme, you have basically a bunch of waves propagating right to left inside of these regions, and then you can impose certain boundary conditions. So, for example, on the left region, you can impose that you have no propagation because you have the mirror, and then you try to see what the electric field is at the end of the mirror. And so, to go back to your question, so these discs are going to be in the order of millimeters, and so this is because they have to have at least half the wavelength of the frequency that you're trying to detect. So this gives you an order of microelectron volts for the masses that you're trying to reach. So you can position your disks in different positions and calculate this boost factor function, which will depend on your frequency, and you can basically optimize your system to whatever you want. So because we have this area law, which tells us that the area under this boost factor curve will be always the same, we can position the disks in order to have a boost factor that is either higher, so you'll have bigger enhancement, but you'll have a very narrow bandwidth, or you can have a lower boost factor, but this means that you'll have a bigger bandwidth, and you don't need to constantly be tuning the system in order to cover the entire frequency space. And so you put your disks in a certain position, you wait for a little bit until you take enough data, and then you change the position of the disks in order to cover another part of the parameter space. And this is really nice because at the end of the day, if you cover this space and you find a candidate for the Axion, what you can do is optimize the system to have a lower bandwidth and higher boost factor, and really check if this corresponds to an Axion peak or not. So another consequence of this area law is that the more number of disks you have, the bigger area you have. So for us, it's very convenient to have as many dielectric layers as possible, because this will increase our boost factor and allow us to get higher sensitivity. Now we can do simulations for this. So if we do 1D simulations for material with dielectric constant 24, there's a material that has this dielectric constant. It's lanthanum aluminate, and we position 80 disks. This allows us to obtain a boost factor of the order of 10 to the 4th, which, if you remember from our signal to noise equation, is exactly what we needed in order to have a signal to noise ratio of the order of 1, and then be able to detect something that stands out from our background. Now, we also can do 3D simulations. We do this with finite element methods, but of course one can never simulate the entire system with these simulations, because they are very CPU costly, require a lot of memory. So what we end up doing is certain approximations, and we get some losses compared to the 1D system, but it's still enough to keep this concept going. So the order of magnitude is still the same. Now, one thing is simulations, but you also want, if you build a system, you also want to know what this boost factor is. The problem is that this boost factor is related to the existence of axions. So you're saying that it's basically the ratio between the power coming from your entire booster and the power coming from the mirror. But if there's no axions, you cannot measure a boost factor. So what we do is basically relate our boost factor with quantities that we can measure. And so we do this by doing reflectivity measurements and group delay measurements. And we can infer from there the position of our boost factor in the frequency space. And as you can see on the figure from the top, we have simulations matching very well the measured behavior. So I'm part of this collaboration called MADMAX, which stands for Magnetized Disk and Axion Experiment. It's a collaboration that was born in 2017. And right now we are 9 universities and institutions, mostly in Germany, but also in France and Spain with the University of Zaragoza. And this is a scheme of what a full-size MADMAX would look like. So basically you have your 80 adjustable dielectric disks. They are inside the cryostat that will go to temperatures of liquid helium, so 4 Kelvin, and it will all be surrounded by a 9 Tesla dipole magnet. And it's a dipole because I don't know if you remember, this magnetic field has to be parallel to the disks. So this makes things a bit more complicated. It's not as trivial as doing a solenoid. And this is actually one of the biggest technological challenges that we have to get a 9 Tesla field in order to have a good stimulation of the conversion. And so we can move these disks, we can look at the frequencies that we are interested in. The copper mirror will be placed on one side, and then the radiation will be emitted to this focusing mirror. And then from the focusing mirror, it goes to this horn antenna and to our receiver system. So we have many challenges. Mostly they are technological. So as I mentioned before, we have this 9 Tesla magnetic field, which has to have a quite big bore because it has to house these 1 square meter disks as well as the cryostat. It has to be somewhat long in order to be able to place as many disks as possible. Then we need a very precise system to move the disks. We are talking about differences of micrometers completely destroying our boost factor. So once we optimize the system to have a certain boost factor at a certain frequency, we really need the disks to be precisely placed. And then we have our cryostat, which will also be quite big, and it has to hold these 4 Kelvin temperatures for a long period of time. And then in the middle, you have as well the disks. So these materials that we are hoping to use for the experiment are quite large and very thin. So it's very hard to grow dielectrics of this size. So one of the things that we are investigating is if we can glue together a bunch of dielectric disks that are cut in small pieces. And this is still work in progress. Yeah.
Thanks. So I didn't quite understand, why do the disks need to be so large in diameter? Could you not just, I'm just thinking you could use more disks with a smaller area.
I don't know if it is, where is it? Here. So if you notice, the signal to noise ratio goes with the area.
With the area.
So
But
the
then,
bigger area, the bigger conversion factor you have. The more places that you have in your interface to stimulate the conversion between axions to photons.
but if I just have more disks, then doesn't that have the same effect?
Yeah, in a 1D simulation, yes. The problem is that in 3D you start getting a lot of losses, and then you also get uncertainties from the positioning of the disks. You get more uncertainties from, I will talk about also the thickness variations, the surface roughness. So if the disk is not completely flat, if it's tilted. So increasing the number of disks in 1D makes a lot of sense. But practically speaking, even 80 disks is quite a challenge.
Okay, thanks.
So we saw that all of this conversion is based in this Axion induced electric field, which goes with the inverse of the dielectric constant. And so we ideally want a disk that has as high dielectric constant as possible in order to have a larger discontinuity and have a higher axion to photon conversion. But at the same time, we also need a material that has very low loss. So we want to reduce, it's a big effort to create these photons. We don't want to lose them as they travel through all of these layers. So we have two candidate materials. One of them is sapphire, which has a dielectric constant of 9.4. And so far, we have been able to purchase discs which have 30 centimeters. Lanthanum aluminate would seem like a better candidate, but it's much more difficult to grow discs of lanthanum aluminate to the sizes we need. So far, sapphire looks for us to be the best candidate in order to create the system, but we are still under investigations to see if we can glue these discs together and have a system with higher dielectric constant. So as I was talking about before, these discs are 1 millimeter and very small imprecisions on the shape of these discs can completely change the shape of your boost factor. So you have factors like thickness variation, surface roughness, disc tilting, which in the order of micrometers can completely ruin your boost factor and ruin the conversion that you need. So I think this also explains a little bit the challenge of having more discs.
Sorry, a short question. This problem, I guess it's higher for bigger discs. So the larger the disc, the stronger is the specification on these deviations.
I think so as well, because you grow these discs and then you cut them, but then you also position them. They are 1 millimeter thick. So gravity effects, and we're talking about micrometer variations. So there for sure, larger discs are also a complication in that sense. So if we look into our parameter space and we project what MADMAX is trying to build, so 80 dielectric discs with 1 square meter area inside this 9 Tesla magnetic field, and with a system temperature of 8 Kelvin, we can get very close to these QCD lines in the range of 40 to 400 microelectron volts. And this constitutes still an unexplored range in our parameter space. So the experimental site is planned to be at DESY in the North Hera Hall, where the previous H1 detector was. So you can see on the right a picture of the yolk of the previous detector, and the plan is to put inside our magnet, and MADMAX will be inside of it. And this is the timeline that we have. So as I said before, the collaboration was founded in October of 2017, and the goal is to get a full MADMAX at DESY in 2028. And for that, it's still a long road. And at the moment, we are in the prototyping phase. So we have a bunch of prototypes testing different components of the system. We have the cryogenics prototype. We have mechanics prototype to test how precise our disk placement is. And we also have closed boosters to serve as test of principle that we can actually use this technology in order to detect Axion dark matter. So now I would like to tell you a little bit about one of our prototypes, CB100, which stands for Closed Booster 100. It's a 100 millimeter sapphire disc booster. So it's composed of 3 discs of sapphire, which are fixed in position. So we don't move these discs. They are placed with these spacing rings here that fix the position of our dielectric discs. We have a copper mirror at one end, and then at the other end, a parabolic taper, which will couple to the Axion mode that we are trying to detect. So as I said, this is a 100mm sapphire disc with dielectric constant 9.4, and it's optimized for a boost factor of around 2000 with a bandwidth of 50 megahertz. And so we simulate our boost factor, and we also can get very good relation between experiment and simulation in terms of reflectivity and group delay, and localize our booster peak and be sure that what we are looking for is what we want. So early this year in March, we took CB100 to CERN. We brought it here to the north area where the Morpurgo magnet is. This is a 1.6 Tesla magnet. I think it was built in the 70s, and they say it's still the biggest warm bore 1.6 Tesla magnet in the world. So it's quite impressive that they still preserve it and it still works quite well. And we took CB100, we placed it inside. You cannot see it here. It looks, CB100 is very small. It looks a bit ridiculous inside such a big magnet, but this is what we had, and we used it. We have our booster here. It's connected to an LNA. The LNA is connected to an RF cable, which brings the signal to our spectrum analyzer, which will do an FFT and show us the spectrum in terms of frequency. And you might ask, why the hell is this RF cable so long? Turns out that the spectrum analyzer has highly magnetic components, so it has a Higgs filter, and in order not to destroy it, we just put all of our electronics as far away as possible from the magnet. So we took data, and we still need to analyze it, but we can already do a projection for our sensitivity. And as you can see, we get pretty close to the cast limit, still quite far away from the QCD Axion, but as a proof of principle, this is quite nice. And also because it has a lot of, it looks good for the future because we can improve in a lot of things. So for example, the time we can improve on, the system temperature, the measurement was done at room temperature, so we can bring the temperature to lower values and get a bigger signal. And so CB100 is still a very good instrument to use as an Axion dark matter detector, and we hope to be able to do this next year again at CERN and take some more data with it. So another activity that we did at CERN this year was in collaboration with the cryogenic team at CERN. They built this G10 cryogenic chamber, which will have enough size to host our CB100. And we tested many components of the cryogenics. So we brought a mock-up of CB100 with one sapphire discs, with an LNA that was broken, with a copper mirror, and we put temperature sensors in all of these components, and the results were quite nice. On all three sensors we got pretty similar temperatures with variations in the order of 0.3 Kelvin. We needed approximately 7 hours for cooldown, but this is still not an optimized procedure, and so we can improve on that. And we were able to have 23 hours of stable conditions below 10 Kelvin. So it seems like maybe next year we can come back to Morpurgo and keep testing our CB100, maybe put it in this G10 cryogenic chamber, and then hopefully use as well CB200. So CB200 is another prototype that is at the moment in Munich and is under reflectivity investigations, and which will have a much higher conversion power than CB100. So the conclusions: Axions could solve the strong CP problem and reveal the nature of dark matter. Dielectric haloscopes are a very good technology to be able to detect this axion dark matter through axion to photon conversion. MADMAX will be hopefully capable to explore this range between 40 to 400 microelectron volts and get to this QCD line. We took data with CB100. This is very good progress. It's a very big step forward, and we hope to continue with our prototyping stage and keep taking data at Morpurgo and continue with very good results in the future. Thank you.
Thank you very much. Any questions?
Thank you. It's very interesting. I didn't quite understand how you tune. Is it you just decrease the distance between each disk simultaneously?
Mm-hmm.
Okay.
So you basically are doing constructive interference of electromagnetic radiation. So you change the positions. You can imagine just a mirror and a dielectric disk, and you have production of a certain frequency. So you can adjust the dielectric in order for this superposition to be constructive or destructive.
And you move all 80 disks at once?
Well, it depends on the frequency that you want to get. You actually don't, or you try to minimize it as well as much as possible. We are using piezo motor to move the disks.
Mm-hmm.
These break very often, so you have to find ways as well, if these piezo motors break, to be able to find optimal positions of the disks to get the boost factor you want at a certain frequency.
Okay.
So you move as little as possible to get the amplification you want in the frequency range you want.
Okay. And the boost factor can't be measured directly?
Well, it's the ratio of the power you get from axions from one mirror and the entire system. So if you don't have an axion, you cannot measure the boost, the conversion coming from a mirror and from the system.
Okay, okay.
But you can relate the reflectivity and group delay, because the resonances will be in the same positions for these quantities.
Hey, so I think I might have misunderstood something. So you tune the frequency by changing the periods between the disks?
By changing the
period between the disks?
You change the positions of the disks, yes.
Okay. So like the position of all at once, or do you like stretch them out and
you have your disks, you change one disk or change two disks. Like you can optimize with simulations the positions of the disks and also see how.
Okay, it's just that there was a slide that was talking about this change in narrow boost factor as opposed to a wide one in a smaller one in a wider frequency range. Is that related to the period, to the distance between the disks as well? So you tune, you change both frequency and boost factor by doing that.
You change the positions of your disks, and then in a certain frequency range, this will change the boost factor.
Okay.
So, because if you think about it in terms of waves, for a certain position, you'll have constructive interference for certain frequencies, but destructive for another. So you optimize a certain frequency range to have constructive interference in the frequencies you want. And you do this by changing the positions of the mirror.
And does that affect the thickness of the disk as well? So is there any conflict between changing the frequency and having the thickness of the disk be static?
The thickness of the disk we cannot change. We have disks that are inside these chambers, and
so like is there like a limit on the band in which you can tune the frequency that comes from the fixed frequency, fixed thickness alone?
So this is why our range is
Okay,
this
I see.
40 to 400 microelectron volts.
Any more questions?
So you have told us how important is the position of the disk to know the boost factor. When you will move this 80 disk, will you be able to monitor that you are in the position that you want to be? Because I suppose if you move it once and you move it 100 times, maybe the disk will have deviated from what you wanted. Is this?
We have lasers to be able to detect the positions of the disk. So we're working on a system that tracks the positions with lasers.
Okay, thanks.
So I have a question about the width as well. So in this plot, you show the width is 50 megahertz for some frequency, like on the order of 10 to 100 megahertz for some frequency at 100, roughly 100 micro EV, right? For this one.
Can you repeat? Sorry.
So yeah, so I have a question about the width. So here you're showing the width on the order of 10 to 100 megahertz. For some frequency, frequency is 100 micro EV, actually here, 20 gigahertz, right?
Yes.
Yeah. So in your later equation, the prototype CB 100, can we go to that equation?
Yes.
Thanks. I remember seeing a very small width. Yeah, so here your width is 20 kilohertz. Is that the width? Or so you see, yeah, so I don't quite understand like
This
what's
is
going on.
the bandwidth of your Axion peak.
Yeah, so I thought here maybe you should put not the Axion bandwidth, but your response width, I think.
No, this is why do you think that?
Why do I think that? Because usually the broader ones, right? You cannot resolve the Axion width with your broader one. So that's not a bad thing because you have more access to different Axion mass, if you like. That's what I noticed. So
yeah, but these are two different things, because what the other bandwidth was the bandwidth in which you had this enhancement of the power. And this bandwidth is the bandwidth of your Axion peak, which comes from the dispersion relation and the velocity of
yeah,
the
let's
Axion.
talk offline, but I think you do have like slightly more boost here. Like you have a little, so for the same boost, you have a bigger response, I think.
For the
same boost, yeah, for the same beta square 2000, which is roughly what you had before. I think you have a larger response than what you showed here. That's what I think.
For the beta 2000, you have a higher response.
Yeah, let's talk offline. I'm just looking at your two plots.
Yeah, okay. I'm not understanding the question. Sorry.
Any other question? So I understood the prototype that you tested, they have a few fixed discs.
Mhm.
The next one, the CB200, will have
Also
Demo?
fixed discs,
also fixed.
but 5 sapphire discs with
Okay.
double the size. But it's still a fixed disc system.
When do you plan to have a movable disc to test the?
Well, we have prototypes that test the movement of the disc, but I don't know. I think this is still a little bit far away in the future to integrate both systems, and
Okay, so I
It's-
think,
it's actually not that trivial to be able to measure experimentally the boost factor. And we have a lot of difficulties in measuring it with fixed positions. So moving the discs increases even more the difficulties. So at the moment, there's a postdoc in Munich who is trying to do these boost factor measurements and find an optimized position of the discs in order to have a high boost factor. And it's taking him quite a long time to do this. So increasing the level of difficulty, it's still.
okay. Okay, so I think